Hey, welcome back to STEM Online Academy. My name is Jason Masterakos, and for those of you who don't know, my channel is all about advanced mathematics and physics, and how to uh, help undergraduate students uh, enrich their studies in these areas by strengthening uh, where to use these applications, strengthen their applied mathematical skills, their strengthening their critical thinking skills, and strengthening their visual spatial skills when it comes to problem solving concepts. Okay, especially in calculus, physics, and ordinary differential equations. All right, so let's get right to it. I'm not going to get too into it. All right, in terms of anything else. So what we're going to do is this is going to be one of the most confusing ideas in when it comes to calculus and physics, and it's exactly where many students actually lose confidence. Okay, they're going to lose confidence in a certain type, these certain types of integrals. We've seen them before, um, but I feel like it's something that I need to reiterate because uh, integrating these can be a bit annoying. Okay, so we need to go through it again, right? So this video, I'm going to build your visual intuition to explain why certain oscillatory integrals converge while either others don't, right? So I'm not just going to, you know, just tell you, um, we have this integral here and whatever. I'm going to pretty much get into why the integral, uh, why some oscillatory integrals converge while others don't. They behave weirdly, okay? So let's get right into it. All right, so give me a moment. All right, so we're going to be looking at, okay, let's see the volume here. Yeah, we're good. All right, so here's a question that confuses almost every undergraduate student the first time they see it. And I'm sure you can agree, even if you're not in that category. Okay, so here's a question. Okay, so question. So here's the question. Just one sec. Question. Here's the question. And that question is the following, right? Why does, so why, it's a conceptual question. Why does, second here, why does, so why does this integral, right? Integral from 0 to infinity of sine x dx, x dx, diverge, okay? So diverge, okay? Why is it diverge, right? But on the other hand, but we have this integral, I'm going to highlight it, integral from 0 to infinity of e to the power of negative a x sine bx dx, okay, converge, okay, so converge, put that here. So why does this one converge? Okay, converge. Okay, so that's what we have to ask ourselves. Why the first integral diverges, but the second integral will converge. Okay, so most students are told what to do here. Integration by parts, Laplace or Laplace transforms. Okay, use either one, but they're almost never told why one works and the other one doesn't. Right? What's the reason? Okay, why this works but something else doesn't? Okay. So what I'm going to show you in this video is we're going to build the answer visually and logically, okay? So this type of problem stops being scary and starts making much more mathematical sense, okay? So let's go to the next page. All right, so let's go here. Okay, So let me write both integrals side by side. So we have this integral, okay, so integral 0 to infinity of sine x dx, okay, and we have this guy over here, okay, this integral in yellow, integral from 0 to infinity of e negative a, just 1 second here, e to negative a negative ax, right, sine bx dx, bx dx, okay. Let's start with a misconception that many students think divergence is here about the sine function itself, okay? Now, that oscillation somehow, right, is going to cause problems, okay? But that's not the real issue, okay? Oscillation alone, right, does not determine convergence. Let me repeat again. Oscillation alone does not determine convergence. What matters is whether those oscillations can be controlled, okay? So let me get more into it. Okay, let's look at this graph here. Okay, I'm going to make a graph, a very basic graph that you should all know. Okay, it's a sine graph. Okay, here's a sine graph. Right, and we're going to use maybe yellow here, and we'll use white for the curve. Okay, so if we draw a sine graph from x equals 0, right? So from x equals 0 to, let's say, 2 pi, right? It's our domain here. Let's say this is 1, this is -1, right? Then we got 0, and then we got, or let's say pi over 2, right? So it's pi over 2, pi over 2, every 90-degree radians, right? So pi over 2. Then we're going to go, another ones would be pi, right? Then it should be 3 pi over 2, right? 270 degrees and degrees, and then go to 2 pi. Okay, so here is my curve. I'm just putting it in. All right. Back up here, it's periodic, it's a periodic function. Okay. And you can see here now, I might just sketch like this. So as I said, this is a sine curve going on the domain from 0 to 2 pi radians. Okay, as you can see here, this is y equals sine x. Okay, this is y equals sine x. Okay, let's look at this graph. Now, this sine function oscillates. It should oscillate forever. Okay, if we were to actually make a simulation of it, we can show that it's oscillating forever. And you know that its amplitude never shrinks. Its amplitude, when I mean amplitude, I'm talking about this, right? The height here. Okay, to its maximum, right? So from the equation of the x-axis to its maximum there, right? That's the amplitude. And that means that the positive area and negative area never settle down. They keep accumulating without limit. Okay, so as you can see here, right? They're going to keep accumulating without limit. So when we integrate sine x from 0 to infinity, okay, this integral will never stabilize, right? It should be obvious that based on the curve y equals sine x, right, if we were to continue drawing, because in reality it goes on forever, its domain is all real numbers. It doesn't stop from at 2 pi, it continues going, right? So keep going along the x-axis forever, okay? So this integral never stabilizes, and there's nothing forcing the area to die out, okay? So that's what I'm saying here, right? You can see that this integral, right, is going to go as to approach infinity then, right? This integral has no reason to stop growing, okay? That's my point here. As it has no reason to stop growing, something that continues to grow forever, right, is going to approach infinity. Okay, that's what's going to happen here. Okay, This integral has no reason to stop growing. That's why this guy here, okay, is going to be infinite. All right. So I hope that made sense. Now, if we were looking at the second integral, okay, the second one that I've pointed out, right, this guy here, all right. So the second integral, we still have oscillation, but nothing is changed here, okay? Right. The only thing is we've introduced this factor of e to the negative ax. Okay, that's what we've got here. Right? So we still have oscillation, nothing's changed. But now we're just introducing some exponential decay, e to the negative ax, right? Which should look something like this. E to the negative ax, by the way, looks like this. Okay, so let's give me a moment. Second graph here. See that you have a, make this better. Okay, give me a moment. E to the negative ax looks like this. This is y equals e to the negative ax. Y equals e to the negative ax. E to the negative ax. Okay, that's exponential decay, right? And it's decaying. In other words, it's approaching an asymptote, horizontal asymptote at y equals 0, right? Now this changes everything. So as you can see, as x increases, the exponential term forces the amplitude, should force the amplitude of the sine wave to shrink. If we were to combine it as e to the negative ax sine bx, like the graph, that's what would happen. So as x increases, okay, we zoom in on these graphs here, right? So as x is increasing, right? So as x increases, the exponential term forces the amplitude of the sine wave to shrink. Okay, so if you were to draw this, I want you to visualize that yourselves as a challenge, e to the negative ax sine bx, right? Try to visualize the graph, okay? And that graph should actually have the amplitude shrinking, okay, as x increases for the exponential term, all right? So x increases, the exponential term forces the amplitude to shrink. And what ends up happening is that the oscillations won't disappear, they just become irrelevant, okay? That's what's going to happen, right? They just become irrelevant. And this is why our integral converges, okay? So let me repeat again. This integral, right? This integral, okay, as you know, is going to actually, the oscillations won't just don't disappear, right? So oscillations don't disappear. They're going to become more and more irrelevant, okay? And and that's why the integral converges. Not because sine behaves differently, but because the area is being suppressed, right? So as x increases, the amplitudes start to decrease of the sine functions. Okay, and as those amplitudes decrease, right, the oscillations are going to become relevant, meaning that the integral should converge, all right? Hope that is making more sense, okay? Now, this is going to lead to a powerful, powerful principle, okay? You'll use everywhere in your calculus and or physics courses as well, okay? Oscillation does not prevent the convergence, right? But an uncontrollable area does, okay? That's what happens, right? So an uncontrollable area is actually preventing convergence, right? Now, I can prove, I'm sure you guys know how to do this, right? Like the calculation of how the integral of e to the negative ax sine bx dx is, right? But I will compute it, okay? So let's do that. So let's look at blue here. I'm going to compute it is equal to integral from 0 to infinity of e to the negative ax sine bx dx. X dx. Let's calculate this. And the point of calculating is to prove uh, my conceptual reasoning, or my, you can say my conjecture of how I knew that this integral will converge. Okay, so without doing any calculations, I already knew that this, I already had a strong intuition that this integral will converge. However, though, we need to prove it. We need to prove that this interval converges. That means that's to give us a number, right? So let's do that. Okay, so first things first, I can replace this. I can say I is equal to, right? It's always handy when dealing with improper intervals to put a limit. So limit as t approaches infinity, right? Limit as t approaches infinity of integral from 0 to t of e to the negative ax sine bx dx. Okay, it's going to go slowly here. I want to make sure that you guys are understanding what this is, okay? So this takes a moment to digest this, if you need a moment to digest this. Okay. It's always handy if you can sort of, you know, digest it in a moment. So now we've got this, right? So you need to think about how you would integrate something like this. How would you solve a problem of this nature? What tools do we have? What mathematical tools do we have in order to solve it? Well, one thing we can do is integration by parts. Okay, so let we have to choose our u and our dv such that we can integrate after, right? So let u equal to e to the negative ax, right? That means my du is what? Minus a e to the negative ax dx, right? Taking the differential. Okay, then we also have our dv. Now, here's the thing with the dv, okay? My dv, what's my dv? It needs to be sine bx dx, right? So that means my v, my antiderivative of v, of the dv there, okay? If I integrate the sine bx dx, that will give me sine cos be negative 1 over b cosine bx. Okay, we just substitute everything in. Okay, so now we're going to substitute back into our I integral. Substitute. Okay, back into I. I know what I is. Was equal to this that we said, right? Limit as t approaches infinity of the integral from 0 to t, right? 0 to t e to the negative ax sine bx dx. Now we're just using IBP, integration by parts. Okay, so this is now going to be, so I is going to be like this, right? So it'll be the limit as t approaches infinity, okay? All in square brackets, u times v, right? So u times v, so this is going to be, u was e to the negative ax, okay? So u is equal to negative ax, My v was the negative 1 over, 1 second here, negative 1 over b cosine bx, right? So negative 1 over b, this guy over here. I put that in, negative 1 over b, so I'm going to put the negative here, negative over b. Okay, cosine bx from 0 to t. Right, then minus, right, when I say minus, remember it's minus the integral of u dv. Remember it's u times v, this part is u times v, right? So this is u times v. This is u times v, the product of u and v. And then we have minus the integral of v du. So minus integral from bounds are from 0 to t. V was negative 1 over b cos bx and then du, right? So it's going to be minus, right? So minus, be careful with the negatives here. It's very easy to make a mistake, actually. Okay, so negative, right? Negative times negative, right? Negative. A over b. Okay, so a over b, e to the negative ax. Okay, e to the negative ax. Okay, cosine bx dx. Bx dx. Hope you guys are finding this interesting, right? So this is a cool integral. Okay, it's not that bad, but uh, it does take some time to integrate. Okay, so next part here is we're going to use limit again, right? So say limit as t approaches infinity. Okay, then we're going to have over here now, it's going to be minus. Okay, so minus e to the negative ax all over b cos bx. Yeah, make my b better. From 0 to t. Negative is positive, negative, so this is minus a over b because a and b are constants. A over b, I'm going to highlight that for a reason. A over b. Okay? And then you just integrate from 0 to t, e to the negative ax cosine bx dx, all in square brackets. Okay, so this is what we have right now. Now, we're trying to, again, so we came to an integral that looks complicated. Okay, normally this would be a problem. Usually when we do integration by parts, we want to choose our u and our dv such that after, when we plug it into uv minus integral v du, we're able to have the equation integrated, right? However, we can't integrate that directly by easier methods. Okay, so what we need to do is use IBP again. By the way, I'm saying you should be saying IBP the first time. So your justification should be by IBP, right? So by integration by parts. Part one, by the way. Yes, part one gets annoying. Okay, so we're using it the first time. Okay, but we have to use it again because we can't integrate that by using simpler methods. Okay, so let's do that. Let's use IBP again. Okay, so we need to choose. So choose your u and dv. I'm going to let my u, say I'm going to let my u equal to this. U is equal to e to the negative ax. Okay, my du should be minus ae to the negative ax dx, right? I'm taking the differential with respect to x. Okay, now my dv is going to be cosine bx. Okay, which means that my v, if I were to take its antiderivative, would be what? 1 over b sine bx. Okay, so 1 over b sine bx, okay? Hope that is making sense. Now, there's a reason why I chose it that way. It's going to make sense when I do my substitution again. So let's do that. So let's put that back into this equation right here. Okay, so this is going to be equal to limit as t approaches infinity from minus e to negative ax all over b of cosine bx from 0 to t. Okay, that's the first thing. Minus a over b, right? And then we just substitute into this craziness right here, right? So this guy over here, what that integral is in terms of uv minus integral v du. So using what we found here, okay? So let's do that. So we're going to substitute in, okay? So we're going to have minus a over b, integral from 0 to t. So we're going to do that. So u times v. What was our u? Our u was e to the negative ax. Okay, so u was e to negative ax. V was the b, 1 over b sine bx. b sine bx. Limits of integration should be from 0 to t, right? We're replacing that for infinity. And then minus integral of v du, right? So minus, because we have the minus a here, it comes positive. A over b, and then we integrate from 0 to t of e to the negative ax sine bx dx. Let's make this better, actually. X dx. Okay. So fairly straightforward. It's just long and annoying, but I'm going to shorten this here, right? So you have to take, we're just going to use, we just have to collect like terms now, right? And then we'll apply the limits. Limit as t approaches infinity, right? All in square brackets, okay, of negative e to the negative ax all over b cosine dx from 0 to t. Okay. Then what ends up happening, multiply in, okay, let's FOIL it. So it becomes negative a e to the negative ax sine bx all over b squared, okay, plus a squared over b squared, right? B squared, and then you just integrate from 0 to t of e to the negative ax sine bx dx. Okay. Right, so this is what we've got so far. Let's go to the next page. Okay, I'm just going to simplify, right? So continuing, we have the limit as t approaches infinity. Okay, as t approaches infinity in square brackets. Now, we've got all this, right? So if we were to input our bounds from 0 to t, cos of bt, we already know what that would be. I already intuitively helped you guys figure out that a cos or a sine function that is going without bound, because we know that t is approaching infinity. So if you put in t here, cos t, we eventually have to notice that it's going to approach infinity. So cos infinity, well, we already know what that is, right? But e to the negative infinity will be 0, right? This is approaching 0 faster than this is approaching infinity. So this goes to 0. Okay, so the first part is 0. Okay, 0, and then remember that was cos bt. That's when I substituted t in first. Okay, when I substitute t for x everywhere. All right. Now if I substitute 0, right, that just gives me negative 1 over b. So plus positive 1 over b. Okay, so this would be positive 1 over b. Okay, that's the first part. Positive 1 over b. Over here now, right? Substituting t in everywhere, e to the negative infinity, that goes to 0, and t 0, right? So that goes away. Lower limit of integration, yeah, that's a 0. That collapses completely, okay? And then we're just left with the a squared over b squared, right? A squared over b squared, a squared over b squared. Yeah, let me substitute that in. By the way, I'm already evaluating the limit all in one go, so we don't need to put a limit there. Okay, so this is equal to 1 over b. I should write it like this, right? This is 1 over b, right? So 1 over b, okay, 1 over b plus a squared over b squared, right? So plus a squared over b squared, okay? And then we were integrating from 0 to infinity of e to the negative, right? E to the negative ax sine bx dx. E negative x sine bx dx. Okay, sine bx dx. All right. So we've got this. Now, we still have an issue. This integral right here is still hard to compute. This is our second time using integration by parts. However, though, we run into a problem. Okay, so what we have to do is notice how our first thing that we want to integrate was this. This is the integral that we want to solve, right? E to the negative ax sine bx dx. Look how we landed back to this. So you know what that means, right? The left-hand side, this is what we wanted to integrate. But all of this by integration by parts was initially this. I can't integrate this directly, but I can rearrange. If I rearrange for integral e to negative ax sine bx dx, getting the like terms, and then dividing by a factor, then I'll be able to solve for this integral. Okay, so move it to the other side. Okay, so now we have this integral right here. So it becomes integral from 0 to infinity of e to the negative ax sine bx dx minus a squared over b squared integral from 0 to infinity of e to the negative ax sine bx dx. And this is equal to 1 over b. Okay. So obviously what you would do next is factor this guy out, e to the negative ax sine bx dx as a common factor and as a common like term, multiplied by 1 minus a squared over b squared would be the the common inside of the factor here is equal to 1 over b. Divide both sides, and I get what my integral was supposed to be. What's this? Negative ax sine bx dx is equal to, let's see over here. Okay, let me see. It's supposed to be like an e to the negative ax here. I forgot that factor. Okay, so we have that. And what we actually end up getting actually is an interesting result, what this integral actually is. Okay, can you guess what it is? Turns out that this integral is just equal. There's no e to the negative x. What am I doing? Thought there was. No, we're fine, we're fine. We end up having b all over a squared plus b squared. Note that a and b both belong to the real numbers. Okay, these are real numbers. They're constants. Okay, and that is the solution to our integral. Okay. Now, what's the significance of this compared to the method that I used earlier to figure out that it converges? Well, since a and b are real numbers, therefore they're actual numbers, so they converge. This integral converges. Okay, so therefore we've shown that it converges. Converges. Hope that made sense. Okay, so I hope that was handy for showing you that when it comes to integration, right? When it comes to convergence of certain integration problems, you can either solve it through, using some intuitive reasoning, right? Making a conjecture of what's happening to the behavior of the functions, right? And or algebraically going through all this mess. Now, in my opinion, if you have a test, it might be easier to do it this way, like intuitively figure out if it converges or diverges. You save a lot of time, unless they ask you to prove, and then you have to go through all this nastiness. Okay. All right. So yeah, and you can see here, right? I want you to notice that something very important. The answer depends only on the competition between the decay rate, right? The decay rate, right over here. Decay rate A, right? And the oscillation frequency B. Okay, as you can see here. It's not an accident, it's just the structure of the problem. Okay. All right. So we've covered almost everything, right? One last thing, right? This is our menu. I always like to check this off. Is physical interpretation, right? So this exact integral actually appears everywhere in nature, actually. Okay, when it comes to forced oscillations, AC circuits, signal processing, damped systems, this integral is very popular. Actually, it pops up everywhere. So in the language of physics, the exponential term actually has a major physical significance. Actually, the exponential term actually represents energy laws. You don't need to know that, but if you're ever interested in knowing the physical implications of e to the negative ax represents energy loss, just to let you know. Okay. And it makes sense, right? Because here's the verification, right? E to the negative ax is an exponential decay. If it's an exponential decay, the curve has to be going downwards and asymptotically approaching the x-axis. Okay. Well, if it's going downwards, obviously there's a decay. If it was in terms of energy and stuff like that, this would be energy loss, energy decay. Okay. All right. So I hope that is making sense. So once you see it this way, right, the math stops feeling abstract and you're no longer calculating, you're now reading something I like to call behavior, okay, mathematical behavior, as opposed to only calculating. So I showed you two ways: understanding the behavior of the problem, right, from the graphs and the models, versus just calculating and getting the answer. Calculating does take a long time, as you can see. It's annoying. Use the one that is fastest, in my opinion. All right. Lastly, common exam mistakes. Okay, here are common exam mistakes. So I want to put this down, right? So common exam. So common. So these are common exam mistakes. Okay, so common exam mistakes. This is very important. Okay, here are the three most common mistakes students have when it comes to this area. Okay, one, try to integrate sine first. Trying to integrate sine x first. This is bad. Do not do this. Okay, I repeat, do not do that. Never do that. Okay. Number two, forgetting the role of the decay. Number two is forgetting the role of the decay. Role of decay. Okay, that's also a problem. And number three, never do this, is memorizing methods, right? So three is never to memorize methods instead of understanding instead of understanding. Okay, so make sure you don't do this. That's a disaster. Okay, these three things, make sure you are never finding yourself doing them. Okay, if you fix just this one idea, you fix your entire class of problems. Okay, so make sure you just don't do any of the three. This is a nightmare when it comes to doing uh, integral calculus. Okay. All right, so that is it. But before I get going, okay, I do want to mention one thing. Okay, if you want more problems like this, okay, where we focus on mainly structure and abstraction, then my book, Advanced Integration Techniques, is written specifically for strong undergraduates, or undergraduates in general, doesn't matter. Even if you're not strong, there is a section that helps you build on your knowledge, doesn't matter. Who want to go deeper, okay? Or if you want one-on-one help learning how to think this way, right? Not just for this integral, but across, calculus topics, physics topics, whatever, okay? Doesn't matter, all right? Doesn't matter what it is. You'll find tutoring details in the description. There will be descriptions in the description below this YouTube video. There will be two descriptions specifically of how you can either reach me or purchase my book. Okay. All right. So in the next video, I just want to let you know, which will be tomorrow actually. We're going to look at something directly, related to integration, but it'll be interesting. Okay. Have a good night, guys. Thanks again to all of my subscribers. And don't forget, new people, to like and subscribe. Take care.